Welcome back to Droneverse, understanding drones worldwide. You're watching episode 03, and if you have been following this course from the beginning, you already know quite a lot. I am genuinely glad you are here, because today's session is one of the most important in this entire course. We are about to go somewhere most drone pilots never go. Not just understanding that drones fly, but understanding exactly why they fly, how they think, and how the law governs every single flight you will ever make. But before we get there, let us spend a moment with where we have been. Because this course is built like a building, each session is a floor, and you cannot reach the top without every floor underneath you being solid. In Chapter 1, we started from the very beginning. We defined what a drone is, traced why drones exist and how they evolved, and mapped out where they are used today, from the farm fields of Maharashtra to the battlefields of Eastern Europe. We categorized them: consumer drones for recreation and photography, FPV drones for the visceral experience of first-person flight, agricultural drones transforming how India feeds itself, industrial drones redefining how we inspect infrastructure, and military drones reshaping geopolitical power. We also introduced the regulatory landscape, the DGCA in India, the FAA in the United States, ESA in Europe, and understood that flying a drone is not just a technical act, it is a legal one. In Chapter 2, we cracked the drone open. We identified the 7 core subsystems: frame, motor, ESC, flight controller, battery, propellers, and radio, and went deep into each one. We explored carbon fiber frames and how size classes work. We understood why BLDC motors dominate drone propulsion, what KV rating means, and how stator dimensions determine torque. We went through escape operation, D-shot protocols, and signal flow from pilot to motor. We took a serious look at LiPo batteries, the chemistry, the cell structure, the danger, the rules. We then explored the sensor ecosystem, the IMU with its accelerometer, gyroscope, and magnetometer, GNSS, and the 6 global constellations, including India's own Navisi, sensor fusion through the Kalman filter, RTK positioning for survey-grade accuracy, GPS spoofing, and modern drone warfare. That was Chapter 2, the body of the drone, everything physical. Today, we understand the brain. Today, we go inside the flight controller. We understand how it thinks, what software it runs, how it decides what each motor should do at any given microsecond. We will cover PID control, the most important algorithm in the history of autonomous flight. We will compare the major firmware ecosystems. We will learn how the radio link works and how to establish it. We will cover calibration, fail-safes, and the regulations that govern every drone flight in India. And we will end with the 10 golden pre-flight rules that every professional drone pilot lives by. Let us begin. Here is a thought experiment. Imagine you have built a perfect drone. Beautiful carbon fiber frame, 4 perfectly balanced BLDC motors, a fully charged LiPo battery, 4 ESCs wired immaculately, 4 propellers properly attached. You power it up. Now imagine you have no flight controller, just the battery directly powering the ESCs, which power the motors at a fixed, equal speed. What happens? The motors spin. The propellers generate lift. The drone might even leave the ground for a fraction of a second. But the instant any external force acts on it, a gust of wind, a tiny imbalance in the motor speeds, any deviation from perfectly level, the drone tips. Once tipping begins, the higher side generates more lift, which causes more tipping, which causes more lift on that side, which causes more tipping. Within milliseconds, the drone is tumbling. It crashes. Without a brain, a drone cannot fly. Period. This is not a hypothetical. This is physics. A multi-rotor drone is inherently unstable. It requires continuous, active correction to remain in flight. The frame, the motors, the battery, none of them know what level means. None of them can sense when the drone is tipping. None of them can calculate what correction is needed. The flight controller does all of that. It is the brain, And like the human brain, it never sleeps while the drone is powered. Think about what the human brain does when you ride a bicycle. You do not consciously command each muscle. You do not calculate the precise torque required from your left calf versus your right. You do not deliberately analyze the gyroscopic effects of the spinning wheels. Your brain does all of that below the level of conscious awareness, running in the background, making thousands of micro-corrections per second. If you had to consciously control every muscle involved in cycling, you could not do it. It happens automatically. The flight controller is doing the same thing for the drone. While you move the control sticks and tell the drone where you want it to go, the flight controller is managing the continuous, moment-to-moment balancing act that keeps it in the air. You provide the intention. The flight controller provides the execution. Specifically, the flight controller is doing 4 things simultaneously, thousands of times per second. First, it listens to all the sensors, gyroscope, accelerometer, magnetometer, barometer, GPS, and builds a real-time model of the drone's current state. Second, it listens to the pilot's control inputs and translates them into desired state targets. Third, it calculates the difference between the current state and the desired state. Fourth, it determines what change in each motor speed will bring the current state closer to the desired state and issues those commands to the ESCs. That loop, sense, compare, correct, repeat, runs at up to 8,000 times per second on modern flight controllers. Every 125 microseconds. While you are still thinking about moving your thumb, the flight controller has already made 4,000 corrections. This is why skilled drone pilots talk about the flight controller as a partner, not just a component. You handle the big picture. The flight controller handles everything else. Let us open the flight controller itself and look at what is physically inside it. The heart of any flight controller is the microcontroller unit, the MCU. This is the processor that runs the flight control firmware and executes the control loop. For the vast majority of modern drone flight controllers, that processor comes from the STM32 family made by STMicroelectronics, a Swiss-French semiconductor company that has become essentially the standard for this application. The STM32 family is based on the ARM Cortex-M architecture. ARM processors are everywhere in modern electronics. They are in your smartphone, your smartwatch, many laptops. The Cortex-M variants are specifically designed for microcontroller applications where low power, deterministic timing, and real-time performance matter more than raw computing throughput. There are 3 processor variants you will encounter most often in drone flight controllers. The STM32 F4, commonly called the F4, runs at 168 MHz. For years, this was the gold standard of FPV flight controllers. It is fast enough to run the control loop at 8 kHz while simultaneously managing all the communication interfaces. F4-based flight controllers are still widely used today, especially in budget and mid-range builds. The F405 and F411 are the most common specific variants. The STM32 F7, the F7, runs at 216 MHz. More processing power, more memory, more peripheral interfaces. F7-based flight controllers can handle more complex firmware builds, support more connected devices, and process data faster. The F745 and F765 are the common variants in this family. The STM32 H7, the H7, represents current state-of-the-art. Running at up to 480 MHz with 1 MB of RAM and sophisticated direct memory access capabilities, the H7 can comfortably run the control loop at 8 kHz, process video streams for onboard analysis, manage telemetry, and still have processing headroom to spare. The H743 is the chip you find in top-tier FPV flight controllers like the Martek H743, the Kakute H7, and the iFlight Blitz H7. Now, beyond the main processor, a flight controller board has several other critical components. The IMU, which we covered in depth in Chapter 2, is soldered directly onto the flight controller PCB. Common IMU chips you will encounter include the MPU 6000, which was the standard for years, the ICM4 to 688, which offers dramatically better noise performance and higher gyroscope sample rates, and the BMI 270 Bosch entry that is used in many current designs. Some premium flight controllers use dual IMUs to separate sensors that cross-check each other, which improves reliability and allows the firmware to detect if one sensor has failed. The barometer is also typically integrated on the flight controller board. Common choices include the BMP 280, MS 5611, and DPS 310, as we discussed last session. Then there are the communication interfaces, and these are what physically connect the flight controller to all the other systems on the drone. UART, Universal Asynchronous Receiver Transmitter, is the workhorse of drone peripheral communication. It is a simple, reliable, widely supported serial protocol that sends data one bit at a time. Each UART port is a pair of connections, TX for transmit, RX for receive. The GPS module connects to a UART. The radio receiver often connects to a UART. The video transmitter telemetry backfeed connects to a UART. The telemetry radio to a ground station connects to a UART. A modern flight controller might have 4 to 6 independent UART ports, each dedicated to a different peripheral. SPI, Serial Peripheral Interface, is a faster, synchronous communication protocol used for devices that need to transfer data rapidly. The IMU chip almost always connects to the flight controller over SPI. Because the gyroscope data needs to be read at up to 32 kHz, far too fast for UART. I superscript to C, Interintegrated Circuit, pronounced I2C, is a protocol designed for connecting multiple devices over just two wires. Slower than SPI, simpler to wire. External sensors like a secondary barometer, a digital airspeed sensor, or a rangefinder might connect via I superscript to C. The motor output pads, labeled M1 through M4 or sometimes M1 through M8 for octocopters, connect to the signal wires of the ESCs. On modern digital protocols like DShot, these are logic-level outputs that carry the digital motor commands we discussed in Chapter 2. The power input pads accept battery voltage anywhere from 3S to 6S or higher depending on the board rating, and typically include a voltage divider that feeds battery voltage to an ADC pin so the flight controller can monitor and report battery level. Understanding this hardware architecture matters because when you build your first drone or your 10th, you are making decisions at every level. Which processor do I need? Do I have enough UART ports for all my peripherals? Will this IMU give me the gyro sample rate I need for 8 kHz operation? These are not abstract questions. They're the decisions that determine whether your build works exactly as intended or becomes a troubleshooting nightmare. So far, we have been talking about flight controllers primarily in the context of FPV drones, manual or semi-manual flight, a pilot with a controller. But there's an entire other world of flight controller hardware designed for something fundamentally different: autonomous operation. Welcome to the world of autopilots, and specifically to Pixhawk. Pixhawk is arguably the most important open-source hardware platform in the history of unmanned aviation. To understand why it matters, I need to tell you a bit of history. In 2009, a group of researchers at ETH Zurich, one of the world's great technical universities, in Switzerland, began developing an open-source autopilot platform. The goal was straightforward but ambitious: build a flight controller capable of fully autonomous operation that any researcher, developer, or engineer could use, study, modify, and improve. They called the software framework RDUPilot, and the hardware platform that ran it evolved into what we now call Pixhawk. The critical word here is open source. Everything about Pixhawk, the hardware schematics, the PCB layouts, the firmware source code, the communication protocols, is publicly available. Anyone can read it. Anyone can modify it. Anyone can build compatible hardware. This is philosophically the opposite of proprietary commercial systems where the technology is locked away and users are dependent on the manufacturer. The open source approach did something remarkable. It attracted a global community of contributors, students, engineers, hobbyists, professionals, military researchers, academic institutions. Over 15 years, that community added support for dozens of vehicle types: multi-rotors, fixed-wing aircraft, VTOL platforms, helicopters, rovers, submarines, boats. They added hundreds of flight modes, sophisticated mission planning capabilities, integration with professional-grade sensors, and support for commercial-grade redundancy features. No single company, however well-resourced, could have built this. It required a community. Today, Pixhawk is the backbone of a massive industry. Survey drones from companies like SenseFly and Wingtra run Pixhawk-compatible autopilots. Agricultural platforms from DJI Agra's competitors use RDU-Pilot or PX4. Research institutions worldwide use Pixhawk as their standard development platform. Many defense contractors and military research programs have Pixhawk-derived systems in development or deployment. The current hardware ecosystem is rich. The Cube Orange, made by QPilot, one of the most respected Pixhawk hardware manufacturers, features an STM32 H757 dual-core processor, triple redundant IMUs, a vibration isolation mounting system, and a modular connector system that makes integration clean and reliable. It is used in commercial delivery drones, agricultural platforms, and industrial inspection aircraft. Holybro makes the Pixhawk 6C and 6X series well regarded for their build quality and sensor selection. Quav produces the X7 Pro series with additional safety features for commercial operations. These are not toys. These are instruments designed for professional duty cycles, carrying payloads worth thousands of dollars, flying missions over sensitive infrastructure. What makes an autopilot different from the flight controllers we discussed for FPV drones? The key difference is autonomy. An FPV flight controller manages stability and translates pilot inputs. An autopilot can execute an entire mission without a pilot. You load a waypoint plan, a sequence of GPS coordinates with altitudes and actions, into the ground control software, upload it to the autopilot, arm the drone, and it takes off, flies the mission, lands, and disarms. You watch. The autopilot handles navigation, translating GPS position errors into flight commands. It manages altitude precisely. It executes actions at waypoints, triggering a camera, opening a payload bay, adjusting flight speed. It monitors its own health and can return to home if communication is lost or battery is low. It can follow terrain using a digital elevation model. It can execute precision landing using visual markers. Show mission planner software screenshot with a planned waypoint mission over a field. Mission planning is the skill that unlocks professional drone operations. In Mission Planner, the ground control software for RDU-Pilot, you can plan survey grids over an area, specifying altitude, overlap percentage, camera parameters, and the software automatically calculates the most efficient flight path. For a 50-hectare agricultural field, Mission Planner will plan a grid flight at 100 meters altitude with 80% forward overlap and 70% side overlap for photogrammetry, calculate the number of images, estimate flight time and battery requirements, and generate the complete waypoint mission in minutes. The drone then flies it automatically. This is what transforms a drone from a toy into a professional tool. The autopilot is what makes that transformation possible. Open source is a philosophy as much as a technical choice, and it has shaped the drone industry in profound ways that deserve a moment of reflection. In traditional technology development, a company develops a product, protects its intellectual property through patents and trade secrets, and charges customers for access to both the hardware and the software. This is fine. It funds research and development. But it also creates silos. If one company develops a brilliant navigation algorithm, another company cannot build on it without licensing fees or legal risk. Progress is constrained by commercial interests. Open source inverts this model. The source code is available to everyone. The hardware schematics are published. Anyone can study the design, improve it, contribute improvements back to the community, or fork it into a new project. The knowledge compounds publicly rather than accumulating privately. Autopilot is perhaps the greatest example of what open source can achieve in engineering. The Autopilot project has contributions from thousands of engineers across dozens of countries. A researcher in India adds a new GPS fail-safe mode. An engineer in Germany improves the terrain-following algorithm. A student in Brazil adds support for a new escape protocol. A defense contractor in the US adds redundancy features. All of this work flows back into the same codebase, available to everyone. The result is a software system of extraordinary capability that no single organization could have built alone. The contrast with DJI is instructive. DJI is a closed ecosystem. The software that runs a DJI Phantom or mattress is proprietary. You cannot read it, modify it, or know exactly what it is doing. DJI makes excellent products. Their engineering quality is genuinely impressive. But if DJI goes bankrupt, or decides to discontinue a product, or changes its pricing model, you have no alternative. The community that depends on that ecosystem has no recourse. With Autopilot, if any company stops supporting the project, the code still exists. The community can continue development indefinitely. Universities can teach from the actual source code. Companies can build commercial products on it and compete on hardware quality and support services rather than on software lock-in. The limitations of open source are real too. There is no single company responsible for support. Bug fixes can be slow if the bug affects a use case that few contributors care about. Documentation can be inconsistent. For a beginner, the complexity can be overwhelming. There is no phone number to call. These are genuine trade-offs, and understanding them helps you choose the right tool for each application. What is firmware, and why is it different from software? Let me start with the 3 layers of any computing system, because this confusion trips up beginners constantly. Hardware is the physical thing. The silicon, the copper traces, the capacitors, the connectors. Hardware does not change. You cannot reprogram silicon at room temperature. Software is the program, the code that runs on the hardware. Software is what we typically mean when we talk about apps on a phone, programs on a computer. Software lives in flexible storage, hard drives, solid-state drives, and can be updated, replaced, or deleted easily. Firmware sits between them. It is software that is permanently installed on the hardware and controls it at the lowest level. It is called firm because it is more permanent than regular software, but not as fixed as hardware. Firmware lives in flash memory, a type of non-volatile memory that retains its content when power is removed. Your router has firmware. Your smart television has firmware. The flight controller has firmware. Here is how the flash memory on a flight controller is organized. There is a small, protected bootloader region, typically a few kilobytes, that is flashed at the factory and is responsible for initializing the hardware and providing a mechanism for updating the main firmware. The bootloader almost never changes. Then there is the main firmware region, hundreds of kilobytes to several megabytes, which contains the actual flight control code and can be updated freely. Flashing means writing new firmware to this flash memory region. This is how you update your flight controller's software, switch between firmware versions, or install a completely different firmware entirely. The most common method for flashing a drone flight controller is through the USB port using a protocol called DFU, Device Firmware Update. DFU is a USB standard that provides a simple, reliable mechanism for writing firmware to a microcontroller. To enter DFU mode on most flight controllers, you hold down a small button labeled Boot while connecting the USB cable. This tells the bootloader not to start the main firmware, but instead to wait for a firmware file to be loaded over USB. In the Betaflight configurator, You click Firmware Flasher, select your flight controller target, select the firmware version, and click Load Firmware and Flash. The software handles the DFU communication and writes the new firmware. The whole process takes 30 seconds to 2 minutes. But what does firmware actually do? What is in that code? For a drone flight controller, firmware contains the entire intelligence of the system. The initialization routines that run at power on, configuring the processor clock, setting up the communication interfaces, initializing the IMU, verifying memory integrity. The sensor reading drivers, the specific code that talks to the ICM4 to 688 over SPI and retrieves the gyroscope data. The filter algorithms that clean the sensor data. The control loop logic. The PID algorithm. The mixer that translates axis correction values into individual motor commands. The USB communication stack. The configuration storage and retrieval. The safety systems. All of that is firmware. When you flash a new version, you're replacing all of that code with a new version that might have bug fixes, improved filter algorithms, new features, or support for new hardware. This is why firmware updates matter. A significant firmware update can genuinely change how your drone flies. Now let me walk you through the entire boot sequence, what happens from the moment you plug in the battery to the moment the drone is ready to fly. Power is applied. The processor's power on reset sequence runs, initializing the CPU, the clock system, and the memory controllers. The bootloader starts and performs a quick check. Is the boot button held? If yes, enter DFU mode. If no, continue to the main firmware. The main firmware starts. It initializes all the hardware peripherals, UARTs, SPI buses, I2C buses, timers, ADC channels. It starts reading the IMU at its configured sample rate. It loads the configuration from EEPROM or flash storage, your PID values, your motor mixer, your rates, your failsafe settings. The firmware then enters its initialization phase. It reads the initial gyroscope values and uses them to establish the zero rate reference. It reads the barometer and records the ambient pressure as the altitude zero reference. It waits for the GPS to acquire a fix if GPS is configured. It waits for the radio receiver to establish a valid signal. When all systems check out, the status LEDs confirm readiness. On most flight controllers, a solid or slowly pulsing LED indicates ready. A rapidly flashing LED indicates a fault condition. Something has not initialized correctly. Only then can you arm the drone and fly. Understanding this boot sequence is practically important. If your drone is taking a long time to become ready, you now know what it is waiting for. If it never becomes ready, you know which stage in the sequence to investigate. Now let us compare the 4 major open-source drone firmware ecosystems. Each one makes different trade-offs, serves different use cases, and has different strengths. Choosing the right firmware is like choosing the right vehicle for a journey. A Formula 1 car is not the right choice for a family road trip, and a minivan is not the right choice for a racing circuit. Betaflight is the king of FPV. Born from the Clean Flight project around 2015, Betaflight was written from the ground up to minimize latency and maximize the responsiveness of manual flight. The entire codebase is optimized for one thing: reading the gyroscope as fast as possible, running the PID loop as fast as possible, and outputting motor commands as fast as possible. Everything else is secondary. Betaflight supports 3 primary flight modes. Acro mode, or manual mode, gives the pilot direct control over rotation rates. When you deflect the roll stick, you are commanding a roll rate, not a roll angle. The drone will keep rolling until you release the stick. This is how FPV racers and freestyle pilots fly. It requires significant skill but offers maximum agility. Angle mode keeps the drone level when you release the sticks, deflect the roll stick, and the drone rolls to an angle, release it, and the drone levels itself. Horizon mode is a hybrid, stable at small stick deflections, but allows acrobatics at full deflection. Betaflight's weaknesses are equally clear. It has no GPS navigation mode. It cannot do waypoint missions. It has no terrain following. It has no autonomous return to home in the traditional sense. It is a pure manual flight firmware with excellent stabilization. For FPV racing, freestyle flying, and filming with manual control, it is unbeatable. For any professional autonomous application, it is the wrong tool. RDUpilot is the Swiss Army knife of drone firmware, or more accurately, the industrial tool chest. It supports more vehicle types, more sensors, more flight modes, and more mission types than any other firmware in the world. RDUcopter handles multirotors and helicopters. RDUplane handles fixed-wing and VTOL aircraft. RDUrover handles ground vehicles. RDUsub handles underwater vehicles. All running on the same core code base. RDUpilot has over 30 distinct flight modes. It supports full autonomous waypoint missions, terrain following, precision landing on moving platforms, formation flying, companion computer integration for advanced autonomy, and compatibility with virtually every commercially available GPS, airspeed, rangefinder, and camera triggering system. It is the firmware choice for professional survey companies, agricultural operations, research institutions, and many defense contractors. The trade-off is complexity. RDUpilot has thousands of configuration parameters. Setting it up correctly for a professional application takes serious study. This is not a criticism. The complexity reflects the capability. But it means RDUpilot is not the right choice for someone building their first 5-inch FPV racer. PX4 is RDUpilot's closest competitor in the professional autonomous flight space. Developed initially by ETH Zurich alongside the original Pixhawk hardware, PX4 has a cleaner architectural design than RDUpilot. It was built from the beginning with software engineering principles like hardware abstraction layers and modular architecture that make it easier to port to new hardware. PX4 is favored by robotics researchers and companies building novel autonomous platforms because the clean architecture makes it easier to integrate custom code. PX4 uses core-ground control as its primary ground station software, a well-designed cross-platform application that works on Windows, macOS, Linux, iOS, and Android. The competition between RDUpilot and PX4 is genuinely good for the drone industry. Both communities are pushing each other forward, and hardware like Pixhawk runs both, so operators can choose based on mission requirements. INAV, inertial navigation, fills a specific niche. It started as a Betaflight fork, but added GPS navigation features, making it the preferred firmware for fixed-wing and VTOL aircraft that pilots want to fly with navigation features, but without the full complexity of RDUpilot. Long-range FPV wings, fixed-wing aircraft flown for fun over long distances, often run INAV. It handles GPS waypoints, return to home, and altitude hold, while maintaining a simpler configuration interface than RDUpilot. The quick comparison is this. Building an FPV racer or freestyle drone, Betaflight. Building a professional survey, mapping, agriculture, or delivery platform, RDUpilot or PX4. Building a long-range fixed-wing for recreational GPS navigation, INAV. Building a research platform where code architecture matters, PX4. The control loop is the heartbeat of drone flight. Understanding it deeply, not just intellectually but intuitively, will change how you think about everything from firmware tuning to hardware selection. Let me walk through each stage. Stage 1. Sense. The flight controller reads all its sensors. The gyroscope reports the current angular velocity around all three axes, how fast the drone is rolling, pitching, and yawing right now. The accelerometer reports linear acceleration and the direction of gravity. The barometer reports current pressure and therefore relative altitude. The GPS reports position if available. The flight controller assembles all of this into a model of the drone's current state, a complete picture of what the drone is doing at this exact moment. Stage 2. Input. The flight controller reads the pilot's commands from the radio receiver or the current waypoint from the mission plan. This defines the desired state what the pilot wants the drone to do right now. In hover, the desired state is 0 roll rate, 0 pitch rate, 0 yaw rate, constant altitude. If the pilot pushes the roll stick to the right, the desired state becomes positive roll rate to the right. Stage 3. Error. The error is the difference between the desired state and the current state. If the drone should have 0 roll rate, but the gyroscope is reporting that it is currently rolling left at 50 degrees per second, perhaps because a gust of wind pushed it, the roll error is 50 degrees per second in the wrong direction. This error value is the input to the next stage. Stage 4. PID. This is where the correction is calculated. The PID algorithm takes the error value and computes how hard to push back, in what direction and with what force. We will explore PID in enormous depth in the next section. Stage 5. Mix. The correction values from the PID controller are expressed in terms of roll, pitch, and your correction's abstract axis. The mixer translates these into commands for each individual motor. For a quadcopter in X configuration, increasing roll to the right requires the left motors to spin faster and the right motors to spin slower. The mixer knows the geometry of the frame and the direction each motor spins, and it calculates the precise combination of motor speeds that will produce the desired total forces and torques. Stage 6. Output. The motor commands are sent to the ESCs via D-shot. The motors change speed. The drone moves. Then the loop repeats. Immediately. Without pause. Without rest. Why does this need to run 8,000 times per second? Why not 100 times per second or 10 times? The answer is physics and the nature of instability. A drone can go from stable to crashing in fractions of a second. A gust of wind begins tilting the drone. If the control loop runs slowly, by the time it detects the tilt and begins correcting, the tilt has grown large enough that the correction overshoots, and then the correction itself needs to be corrected. Slow loops lead to oscillations, instability, and ultimately crashes. At 8 kHz, the loop runs every 125 microseconds. The gyroscope is being read 8,000 times per second. Deviations from the desired state are detected and corrected before they can grow to the point of being perceptible. The drone feels solid, responsive, rock-stable. Human reaction time is approximately 200 to 300 milliseconds, that is 200,000 to 300,000 microseconds. The flight controller corrects errors 1,600 to 2,400 times in the time it takes you to consciously react to something. You simply cannot fly a multi-rotor without it. PID control, proportional, integral, derivative. These three terms might sound like mathematics textbook language, but I promise you, by the end of the section, you will understand PID, not just intellectually but intuitively, in a way that will make you a better drone builder and pilot. Let me start with a story. Imagine you are new to driving. You are on a straight highway, and you are supposed to maintain a speed of 100 kilometers per hour. You watch the speedometer. When you see you are going too slow, you press the accelerator. When you see you are going too fast, you ease off. Simple enough. But let us examine exactly how you make these decisions. When you look at the speedometer and see 90 kilometers per hour, 10 below the target, you feel an immediate, proportional response. I am 10 under. Press the pedal significantly. If you are at 99 kilometers per hour, just 1 under, your response is subtler. I am barely slow. Gentle pressure. Your response is proportional to the current error. This is the P, proportional, term. The proportional correction is simply the error multiplied by a Gann factor. Large error, large correction. Small error, small correction. Here is the problem. Pure proportional control overshoots. You apply firm pedal pressure because you are 10 under, the car accelerates. You watch the speedometer approach 100. You ease off. But you ease off exactly when you hit 100. By then, the car's momentum carries it past 100 to 105, then 110. Now you brake. You overshoot downward to 90. You accelerate again. You oscillate around the target. The D, derivative, term solves this. Derivative means rate of change. The derivative term looks at not just the current error, but how fast the error is changing. If the drone is rolling at 50 degrees per second in the wrong direction, but that error is already decreasing fast, it is already being corrected and will likely be gone within a moment, the derivative term reduces the correction. It is predictive. It says, yes, there is error now, but it is disappearing rapidly. Do not overcorrect. Going back to the driving analogy, an experienced driver does not just react to current speed, they anticipate. When the car is approaching the target speed and you feel it decelerating, you ease off the pedal before the speedometer reaches 100, knowing the car's momentum will carry it to the target. You are predicting the future from the rate of change. That is D. But now there is a different problem. Pure PD control can have steady-state error, a persistent small offset that never fully corrects. The wind is blowing steadily from one side, pushing the drone off course. The proportional term generates a correction. But as the drone approaches the target position, the proportional correction decreases because the error is getting smaller. The drone settles at a point where the proportional correction exactly balances the wind force. This is not the target, it is close, but offset. And it stays there. This is where integral comes in. The integral term sums up all the past errors over time. If there has been a persistent small error in one direction for any length of time, the integral term accumulates that history and adds a growing correction to compensate. It says, we have been slightly off target for the last 2 seconds. There must be a persistent bias, a wind, a motor imbalance, a weight offset. Let me apply an increasing correction to account for it. Back to driving. Imagine you are driving in a steady crosswind. Your car constantly wants to drift to the left. You apply a slight right steering input to compensate. You are not reacting to an error. You are correcting a steady bias. That is your personal I term at work. So PID stands for P, respond to current error. I, correct accumulated past error. D, predict and dampen future error. Together, they produce a control response that is fast, accurate, stable, and robust to disturbances. Now let us translate this to drone flight specifically. The roll axis PID loop is responsible for keeping the drone from rolling unexpectedly. Every time the gyroscope detects a roll rate, a rotation around the roll axis, the PID loop calculates a correction and adjusts the left and right motor speeds to counteract it. In a well-tuned drone, this happens so fast and so precisely that wind gusts of several meters per second produce almost imperceptible wobble. If the proportional gain, the P value, is set too high, the drone overcorrects constantly, producing the characteristic oscillation you see in poorly tuned drones, a rapid, persistent wobbling even in still air. If P is too low, the drone feels sluggish and imprecise, corrections are too gentle, and the drone drifts more than it should. If the derivative gain D is too high, the flight controller starts reacting to noise in the gyroscope signal, the tiny, random high-frequency fluctuations that are present in any electronic sensor. This manifests as a characteristic high-pitched motor whine, the motors rapidly oscillating at audible frequencies in response to noise rather than real motion. If D is too low, the drone will overshoot corrections and produce a bouncier flight feel. If the integral gain I is too high, the drone accumulates corrections aggressively and can wind up building a large integral correction that, when the disturbance disappears, overcorrects dramatically. If I is too low, the drone drifts persistently against steady winds. The practical advice from the slide is worth emphasizing. Default PID values on modern firmware like Betaflight are tuned for typical 5-inch builds and are excellent starting points. For 95% of builds, the defaults work well. Do not tune PID values randomly or because you read an online article saying just raise your P. Only tune when you have a specific symptom, You understand what that symptom indicates about the control loop, and you have logged the flight data to confirm your hypothesis. PID control is not unique to drones. It is used in virtually every control system in the modern world. The thermostat regulating your air conditioner uses PID. The cruise control in your car uses PID. The autopilot in a commercial airliner uses PID. Industrial robots, chemical plant temperature controls, blood pressure regulators in medical devices, all PID. It was first described mathematically in the 1920s and 1930s, and it remains one of the most widely applied algorithms in all of engineering. For drones, it is the algorithm without which flight is impossible. How does the command from your thumb reach the drone? Let us trace the evolution of drone radio communication, because understanding where we came from explains why the current technology is as good as it is. In the early days of radio-controlled aircraft, long before drones as we know them, the control system used PPM, pulse position modulation. PPM encoded multiple channel values, throttle, aileron, elevator, rudder, into a series of pulses on a single wire. The timing between pulses encoded the channel values. Simple, low-cost, adequate for the aircraft of the 1990s. But PPM had a latency of around 22 milliseconds, the time from when you moved a stick to when the aircraft received the command, and range of roughly 1 kilometer in good conditions. For the slow aircraft of that era, this was acceptable. SBus arrived as an improvement. Developed by Footbar, SBus is a digital serial protocol that carries 16 channels simultaneously over a single inverted UART signal. Latency dropped to around 14 milliseconds. SBus became the standard for sport and professional RC aircraft through the 2010s and is still widely used today. Its limitation is range. It is a receiver output protocol, not a long-range radio protocol. CRSF, Crossfire Serial, was developed by Team Black Sheep, a Hong Kong-based FPV hardware company. Crossfire was a complete long-range radio system, transmitter, receiver, and protocol designed specifically for FPV long-range flying. The CRSF protocol running on Crossfire hardware achieved latency of around 4 milliseconds and range of 15 kilometers or more. For the first time, FPV pilots could fly genuinely long distances with very low latency. The limitation? Crossfire was and remains proprietary and expensive. Then came Express LRS, ELRS, and it changed everything. ELRS is an open-source radio control system developed by a community of engineers and hobbyists starting around 2020. ELRS was specifically designed to be the fastest, longest-range, open-source RC link available. It achieves to 2-4 milliseconds latency, matching or beating the proprietary Crossfire, with range exceeding 30 kilometers in idle conditions at a fraction of the cost. ELRS uses LoRa, long-range radio technology. LoRa is a spread-spectrum modulation technique developed by Semtech Corporation that trades data rate for range. By spreading the radio signal over a wide frequency band, LoRa signals can be received reliably at distances and through obstacles that would block conventional narrowband signals. LoRa is used in IoT devices, the same technology that lets a water meter communicate with a utility company from a basement through several floors of concrete now powers drone radio control. ELRS transmitter modules slot into standard FPV transmitter base. ELRS receivers are tiny. Some are smaller than a postage stamp and weigh under a gram. They cost a fraction of comparable proprietary systems. And because the firmware is open source, the community continuously improves it, adds features, and fixes bugs. ELRS is now the dominant radio protocol for the FPV community and is growing rapidly in the professional long-range space. The practical implication: for any new drone build today, unless you have a specific reason to use another protocol, ELRS is the correct choice. Let us spend a moment on ESP now, because it appears in your course kit, and it represents a genuinely interesting approach to drone communication. The ESP32, made by Espressif Systems, is a microcontroller with integrated Wi-Fi and Bluetooth radios. It is one of the most popular microcontrollers in the world for embedded projects because it is capable, cheap, well documented, and has a massive community. But ESP now is something different from standard Wi-Fi or Bluetooth. Standard Wi-Fi requires a router, an access point that manages connections. When your phone communicates with your laptop over Wi-Fi, both devices go through the router. This adds latency and dependency on infrastructure. Bluetooth has better peer-to-peer capability, but it has limited range, typically 10 to 100 meters, and its connection establishment is relatively slow. ESP now is a protocol developed by Espressif that allows to ESP32 devices to communicate directly, peer-to-peer, without any router or access point. Communication happens over the standard 2.4 GHz Wi-Fi radio hardware, but using a custom low-overhead protocol optimized for fast, simple data exchange. In the context of the drone kit you are building, one ESP32 acts as the transmitter, the controller. Another ESP32 on the drone acts as the receiver. Control signals, throttle, roll, pitch, yaw, are sent from controller to drone with latency of approximately 2 to 5 milliseconds. For a basic educational drone kit, this is entirely adequate. The advantages of ESP now are accessibility and cost. An ESP32 module costs $1 or $2. The protocol requires no external radio modules, no licensing, no complex hardware. For educational drones, development platforms, and low-cost applications, ESP now is an excellent choice. The limitations are range. The ESP32 radio hardware is not designed for long range, and practical control range over ESP now is typically 50 to 200 meters depending on environment, and the fact that the 2.4 GHz band is crowded in urban environments which can cause interference. For serious long-range flying, ELRS is the correct technology. For learning, for lab builds, for close-range development, ESP now is clean and simple. Binding is the process of establishing a trusted, exclusive relationship between a specific transmitter and a specific receiver. Once bound, the receiver only responds to commands from that one transmitter, and the transmitter expects telemetry back from that one receiver. Why does this matter? Imagine flying at a competition site with 40 other pilots. All of them have radio systems on similar frequencies. Without binding, without each transmitter-receiver pair having a unique identity, you might receive control commands from the pilot standing next to you, or your commands might affect someone else's drone. This would be, to put it mildly, catastrophic. Traditional binding on older radio systems like Fresky involved a physical procedure: power on the receiver in a special bind mode, then initiate bind from the transmitter menu, wait for the LED confirmation, power cycle both devices. This worked reliably, but required hardware manipulation. ELRS introduced the bind phrase, and it is elegantly simple. A bind phrase is any text string you choose. It might be your name, a random word, anything you like. You enter this exact phrase into both the transmitter and receiver firmware. When the ELRS transmitter broadcasts, it includes a unique identifier derived from the bind phrase. Only receivers with a matching identifier respond. The implications are significant. First, there is no physical binding procedure. You can bind a transmitter to a new receiver by simply entering the same bind phrase in the ELRS configurator. No buttons, no LEDs, no physical proximity required. Second, if you need to fly multiple drones on the same transmitter, all your receivers just need the same bind phrase. Third, if you want to prevent others from connecting to your receiver, use a unique, private bind phrase. It is essentially a password for your radio link. The practical advice: choose a bind phrase that is memorable, unique to you, and unlikely to accidentally match someone else's. Your name plus a number, your call sign, anything distinctive. Keep it consistent across all your equipment. Write it down somewhere safe. If you forget your bind phrase, you will need to reflash your receiver firmware. Before we can trust the sensors to fly the drone, we need to tell those sensors what reality looks like. This is calibration, and skipping it, or doing it incorrectly, leads to flight problems ranging from minor annoyance to dramatic crashes. Let me explain each of the 4 critical calibrations. Accelerometer calibration teaches the flight controller what level actually is. Place the drone on a confirmed, genuinely flat surface. Use a spirit level if you are not sure. With the drone perfectly still and level, initiate the accelerometer calibration. The firmware reads the current accelerometer values and stores them as the reference for zero tilt. From this point, any deviation from those values is interpreted as tilt. Why is this necessary? Because the IMU chip is soldered onto the flight controller PCB and the PCB is mounted in the frame, and none of these mounting operations are perfectly precise. The chip might be tilted by half a degree relative to the frame. The frame might not be perfectly level on the bench. Accelerometer calibration removes all of these systematic errors and establishes a reliable horizontal reference. The consequence of skipping or rushing accelerometer calibration. The drone hovers with a persistent tilt. In angle mode, it will drift consistently in one direction even with stick centered. In GPS mode, it will fly in a straight line but slowly drift in the direction of the miscalibration. This is a very common complaint from beginners. My drone keeps drifting sideways. And in the majority of cases, it is a calibration issue. Gyroscope calibration establishes the zero-rit reference, the sensor reading that corresponds to the drone being perfectly stationary. Unlike the accelerometer calibration, gyroscope calibration happens automatically every time the drone boots. This is why it is critical that the drone is completely still during the boot process. The firmware reads the gyroscope values in the first few seconds after power on and records them as 0. If the drone is on a vibrating surface, or if you are already moving it before it finishes booting, the 0 reference will be wrong, and the drone will perceive rotation that does not exist. The symptom of poor gyroscope calibration is your drift. The drone slowly rotating on its vertical axis even with the yaw stick centered, or the drone attempting to turn in hover without input. Always boot your drone on a still, stable surface and wait for the initialization to complete before moving it. Magnetometer calibration is the most involved of the 4. The magnetometer, the digital compass, needs to sample Earth's magnetic field from multiple orientations to build a complete 3D map of its response. The calibration procedure involves rotating the drone through all 6 major orientations: level, nose up, nose down, left side up, right side up, and inverted. The firmware collects samples in all orientations and uses them to construct a calibration model that compensates for hard iron and soft iron interference effects, the magnetic distortions caused by the drone's own components. The critical rule for magnetometer calibration: do it outdoors, away from metal structures, power lines, reinforced concrete, and any large metal objects. The whole point of the calibration is to sample Earth's magnetic field accurately. If you calibrate indoors near your steel workbench or underneath a fluorescent lighting fixture, you are calibrating against a distorted field, and the compass will give wrong headings in the actual flying environment. The symptom of poor magnetometer calibration is something pilots call toilet balling in GPS-assisted hover. The drone slowly circles around a point rather than holding still. The flight controller thinks it knows which way is north, but it is wrong, so its position hold attempts drive the drone in slow circles. Toilet balling is almost always a magnetometer calibration problem. Escape calibration ensures all 4 ESCs respond identically to the same throttle command. The issue: each escape is programmed at the factory with a throttle range it considers 0 to maximum, and those ranges can vary slightly between units. If escape number 2 thinks 1100 microseconds is full throttle and escape number 3 thinks 1900 microseconds is full throttle, they will respond very differently to the same commanded value. The good news: with D-Shot protocol, Escape calibration is effectively automatic because D-Shot sends actual numerical values rather than timing-based pulses. The numerical value 2047 means full throttle to every D-Shot escape regardless of any throttle range calibration. Escape calibration is primarily relevant when using legacy PWM-based ESCs. A fail-safe is the system that decides what the drone does when something goes wrong. This is not an optional feature. It is a fundamental safety requirement. Every drone you fly must have properly configured fail-safes before it ever leaves the ground. The most common fail-safe scenario is radio link loss. The drone is in the air, and for some reason, the pilot flew out of range, an obstacle blocked the radio signal, interference disrupted the link, the receiver stops receiving valid signals. What should the drone do? Without a fail-safe, the drone simply continues executing the last command it received. If the last command was full throttle flying forward, it keeps going. In most cases, this means the drone crashes into something or flies away and is lost. With a properly configured fail-safe, the drone immediately executes a predetermined response. The most common professional response is return to home, RTH. The drone climbs to a safe altitude if it is not already there, navigates back to the home point recorded at takeoff, descends, and lands. If GPS is not available, the fallback is typically a controlled descent and landing at the current position. The RTH altitude configuration deserves special attention. The RTH altitude must be set high enough to clear any obstacles between the drone's current position and the home point. If you are flying in a park surrounded by 20-meter trees, your RTH altitude should be at least 30 meters. If you set it at 10 meters, the drone will fly through the trees during RTH, and you will be looking for pieces. Low battery fail-safe is equally important. The flight controller monitors battery voltage continuously. When voltage drops to a configured warning level, typically 3.5 to 3.6 volts per cell, the system triggers a warning. When it drops further to the critical level, typically 3.3 to 3.4 volts per cell, the failsafe activates an emergency landing. This prevents the battery from being discharged so deeply that it is permanently damaged, and it prevents the motors from suddenly losing power at altitude due to complete battery depletion. GPS failure failsafe handles the case where the drone is in a GPS-dependent mode, position hold, waypoint mission, and the GPS signal is lost. The typical response is to switch to altitude hold using only the barometer and IMU, which allows the drone to hold altitude and accept manual position control from the pilot without attempting GPS-based navigation with invalid data. In professional and military drones, failsafe design is taken to extraordinary lengths. Redundant flight controllers, a primary and a backup that cross-check each other's outputs. Redundant GPS receivers on separate modules in separate physical locations. Redundant power systems with automatic switchover. Redundant communication links using different frequency bands or protocols. The principle is simple. Any single point of failure should be tolerated without catastrophic result. This is called fault tolerance, and it is the engineering discipline that allows companies to certify drones for flight over populated areas. For your course kit, the essential fail-safes to configure are RTH altitude, RTH trigger on signal loss, and low battery warning and emergency landing. Before any flight, verify that fail-safes are active and correctly configured. The procedure is simple. Walk away from the drone while in a safe test environment. Watch that the fail-safe triggers correctly. Confirm RTH behavior. Do this once per new build and anytime you reflash firmware. In professional and military drones, fail-safe design is taken to extraordinary lengths. Redundant flight controllers, a primary and a backup that cross-check each other's outputs. Redundant GPS receivers on separate modules in separate physical locations. Redundant power systems with automatic switchover. Redundant communication links using different frequency bands or protocols. The principle is simple. Any single point of failure should be tolerated without catastrophic result. This is called fault tolerance, and it is the engineering discipline that allows companies to certify drones for flight over populated areas. For your course kit, the essential fail-safes to configure are RTH altitude, RTH trigger on signal loss, and low battery warning and emergency landing. Before any flight, verify that fail-safes are active and correctly configured. The procedure is simple. Walk away from the drone while in a safe test environment. Watch that the fail-safe triggers correctly. Confirm RTH behavior. Do this once per new build and anytime you reflash firmware. The DGCA, Directorate General of Civil Aviation, is the executing arm. The DGCA implements the policies set by MOCA, issues licenses and permits, sets technical standards, conducts enforcement, and manages the digital sky platform. When you need a remote pilot certificate, you deal with the DGCA. When a drone incident requires investigation, the DGCA investigates. The DGCA is analogous to the FAA in the United States or ESA in Europe. It is the frontline civil aviation authority. The Airports Authority of India, AAI, has a specific role in drone regulation. It manages the airspace classification around airports. When you open Digital Sky and see green, yellow, and red zones on the map, the airport proximity zones, the circles drawn around each airport, are based on AAI classifications. The AAI coordinates with the DGCA to determine where drone operations near airports are permitted, under what conditions, and what approvals are needed. The Ministry of Home Affairs, MHA, controls the security dimension of drone operations. Border areas, military installations, intelligence agency headquarters, critical national infrastructure. These sensitive areas are designated as restricted or prohibited zones by the MHA. The red zones you see on the digital sky map around border regions and security installations reflect MHA designations. Flying in these areas is not just a regulatory violation. It can be treated as a security offense. The interaction between these bodies is straightforward in principle. MOCA sets policy, DGCA implements it through the digital sky platform, AAI manages airport proximity zones, MHA manages security-sensitive zones. When you as a pilot use the digital sky platform to check your flying location, you are seeing the combined output of all these bodies, a single integrated airspace classification that reflects all their respective authority. Digital Sky is one of India's genuinely impressive regulatory technology achievements. It is the online platform that manages all drone-related activities under the Drone Rules 2021 registration, certification, permissions, and airspace monitoring. Visit it at digitalsky.dgca.gov.in. The concept behind Digital Sky is NPNT, no permission, no takeoff. The idea is elegantly simple. A drone equipped with NPNT compliant technology cannot fly without a valid digital permission token from the Digital Sky server. The permission is digital, time-stamped, location-specific, and altitude-limited. The drone's onboard systems verify the permission before arming. If there is no valid permission for the current time, location, and altitude, the drone will not arm. Why is this powerful? Because it makes compliance automatic rather than voluntary. In a purely honor-based system, a pilot who chooses to ignore the rules can fly anywhere. With NPNT, the hardware itself enforces the rules. The drone physically cannot operate in violation of its permissions. The registration process for operators is done entirely on Digital Sky. You create an account, enter the drone's details, manufacturer, model, serial number, and receive a unique identification number, UIN. This is the drone's registration, analogous to a vehicle's registration plate. The UIN is stored digitally and verified through NPNT. The airspace map on Digital Sky is an interactive, real-time map of all Indian airspace, color-coded into green, yellow, and red zones. Before any flight, you check this map at your planned flying location. Green means you can fly up to 120 meters without requesting permission. Yellow means you need to apply for permission through the platform. Red means you cannot fly there. The platform also manages permissions for yellow zone flights. You can apply directly through Digital Sky, specifying the location, date, time, altitude, and purpose. The application goes through automated checks against flight information regions, airport traffic zones, and security restriction databases. And in many cases, a permission can be issued automatically within minutes. For commercial operations, Digital Sky is also where you register your remote pilot certificate and link it to your operator account. This creates a traceable record. Every commercial flight you conduct is linked to your identity and your drone's UIN. The practical workflow before any flight: open Digital Sky, navigate to the airspace map, zoom to your flying location, confirm the zone color. If green, you are cleared to fly up to 120 meters AGL. If yellow, apply for permission. If red, do not fly. This takes 2 minutes. Make it a habit. The 3-zone airspace classification on Digital Sky is not arbitrary. Each zone reflects a real calculation of risk: the probability of a drone collision with a manned aircraft, the consequence of a collision, and the sensitivity of the ground below. Green zone: no permission required for flights up to 120 meters AGL. These are areas where drone operations pose minimal risk to manned aviation and to people on the ground. The vast majority of India's land area, rural areas, agricultural land, most semi-urban and urban areas outside airport proximity zones, is green. Your training field should be in a green zone. If it is not, you have a problem that needs to be solved before you fly. The 120-meter AGL ceiling in green zones exists for a specific reason. Manned general aviation, light aircraft, helicopters, air ambulances typically operate at 150 meters and above in uncontrolled airspace. By restricting drones to 120 meters, the regulation creates a 30-meter separation buffer between the drone operating ceiling and the minimum manned aircraft altitude. This is not a coincidence. It is a deliberate safety margin. Yellow zone: permission required from air traffic control or the DGCA before flying. Yellow zones cover the airspace immediately surrounding controlled airports, typically a 12-kilometer radius from the airport reference point, though the exact dimensions vary by airport category. They also cover urban centers beyond certain population densities, flying above 120 meters anywhere, and certain other designated areas. Flying in a yellow zone is not prohibited. It just requires advanced planning and approval. If you need to fly near an airport for a legitimate commercial purpose, aerial photography of a building that happens to be near an airport, for example, you apply through Digital Sky, your request is reviewed, and if approved, you receive a time-limited permission. This process exists because airports are extraordinarily sensitive. Even a small drone strike on a commercial aircraft engine can cause catastrophic damage. Red zone: prohibited. No flight under any civilian circumstances. Red zones cover the immediate vicinity of airports, typically within 5 kilometers of the runway threshold, military airfields, military installations, the borders of India, nuclear power plants, critical infrastructure facilities like major power stations and refineries, and strategic government locations including Parliament and Rashtrapati Bhavan. Flying in a red zone is not a permit violation. It is a potential criminal offense. The Aircraft Act 1934, the Criminal Procedure Code, and anti-terror legislation all have provisions that can be applied to unauthorized flight in sensitive areas. The penalties range from fines to imprisonment. And under the post-9/11 global security framework that India has adopted, flying a drone over a military installation or near a nuclear facility can attract serious charges. The rule is absolute. If it is red, it stays on the ground. India's Drone Rules 2021 represent a significant liberalization and modernization of the earlier regulatory framework. The previous rules, the UAS Rules 2021, which replaced the 2018 civil aviation requirements, were criticized as overly restrictive and difficult to comply with. The 2021 rules incorporated extensive industry feedback and produced a framework that is more permissive than comparable regulations in Europe or the United States for many use cases while maintaining essential safety standards. Let me walk you through the key provisions every drone pilot in India must know. UIN, Unique Identification Number. Every drone above the nano category, which is 250 grams or below, must be registered and receive a UIN through the Digital Sky platform. The UIN is the drone's legal identity. Flying an unregistered drone that requires UIN is an offense. The UIN is valid as long as the drone is in service and the registration is maintained. Fee, minimal. Process, entirely online through Digital Sky. RPC, Remote Pilot Certificate. Any person who operates a drone commercially for any purpose where compensation is received or a commercial service is provided must hold a valid remote pilot certificate. The RPC requires the applicant to be at least 18 years of age, to hold a medical fitness certificate, to pass a theoretical knowledge examination covering air regulations, meteorology, navigation, and drone operations, and to complete a practical assessment. The RPC is issued through DGCA-approved training organizations. An important clarification: the RPC requirement applies to commercial operation. Recreational flying of registered drones by adults does not require an RPC. However, operating any drone without understanding the regulations is risky, and for anyone planning to work professionally in the drone industry, the RPC is the baseline qualification. 120 meters AGL. The altitude ceiling in green zones. As discussed, this is the maximum altitude for drone operations without permission in green zones. This is measured from the ground directly below the drone, above ground level, not above sea level. If you are flying in hilly terrain, the 120 meters AGL ceiling follows the terrain, not a fixed altitude above sea level. VLOS, Visual Line of Sight, is a requirement that the remote pilot must maintain a native visual contact with the drone throughout the flight. You must be able to see your drone with your naked eye, not through binoculars, not through the FPV camera, not through any optical device. If you cannot see the drone, you are not in VLOS, and you are in violation. BVLOS, Beyond Visual Line of Sight, operations require special DGCA approval and are currently only available to authorized operators for specific use cases. Daytime operation. Commercial drone flights under the current rules must be conducted during the day, defined as civil twilight to civil twilight, which includes some time before sunrise and after sunset, but excludes night operations. Night flying requires specific approval. NPNT, no permission, no takeoff. As discussed, the drone must have a valid digital permission for its planned operation before it can arm. This is enforced through the Digital Sky platform. Insurance. Commercial drone operators must carry third-party liability insurance. This protects against claims arising from property damage or personal injury caused by the drone. Basic policies are available through several insurance providers in India at reasonable premiums. Regulations exist because people have been harmed, or because we can clearly foresee how people could be harmed. This is not theoretical. Let me give you real-world examples of what happens when drone regulations are violated in India. The Red Fort incident in 2020 is perhaps the most cited example in Indian drone regulation discussions. A pilot flew a drone in the restricted airspace around the Red Fort complex in Delhi, a designated red zone, situated near critical government and security infrastructure. The pilot was arrested and charged under provisions of the Aircraft Act, the Anti-Hijacking Act, and the Criminal Procedure Code. The charges related to the potential threat to public safety and national security infrastructure. This was not a fine. It was a criminal prosecution with potential imprisonment. Why were the charges so serious? The Red Fort sits in the heart of Delhi, near Parliament, near multiple government buildings, near military and paramilitary installations. The security infrastructure in that zone is designed to protect against threats. An unidentified drone entering that zone, regardless of the operator's innocent intent, cannot be distinguished from a hostile drone by the security personnel monitoring that airspace. The response to such an incursion is automatic and can be severe. Airport disruptions caused by drones are a serious and growing problem globally, and India has not been immune. Drones flying near airport approach paths force air traffic control to delay or reroute incoming and outgoing flights. Each such disruption costs airlines money, frustrates passengers, and creates safety risk. The operator responsible faces criminal charges under aviation law, civil liability for the costs caused, and permanent disqualification from operating drones. In 2019, drone incursions near Mumbai's Chhatrapati Shivaji Maharaj International Airport caused multiple flight delays. Privacy violations are an increasingly common drone offense. Flying a camera drone over private property, recording individuals without consent, hovering near residential windows, these violations have resulted in FIRs under various provisions of Indian law, including the Information Technology Act. Victims of drone-based privacy invasion have successfully obtained court orders for drone seizure and compensation. The consequences of violations are real and escalating. The Drone Rules 2021 set fines of 10,000 rupee to 1 lakh rupees for regulatory violations. Flying in a red zone is a cognizable offense under the Aircraft Act, meaning police can arrest without a warrant. Causing bodily injury with a drone triggers personal civil and criminal liability. And the Digital Sky NPNT logs create a permanent, tamper-proof record of every flight made by a registered drone. Prosecutors can use these logs as evidence. The message is simple. Drone regulations in India are not burdensome, especially compared to equivalent regulations in Europe or the United States. They are reasonable, they are implementable through a free online platform, and they exist to protect people. Follow them. Not because you might get caught, but because the rules make sense. Every professional in high-stakes fields has a checklist. Surgeons have pre-operative checklists. Commercial pilots have pre-flight checklists. Astronauts have launch checklists. The purpose is always the same. Human memory is fallible, especially under stress or excitement, and a systematic checklist ensures nothing important is forgotten. As drone pilots, our pre-flight checklist is the 10 golden rules. Do these in order. Every flight. No exceptions. The day you skip a step because you always do it right is the day something goes wrong. We have covered extraordinary ground today. Let me bring it together one final time. We started by establishing why the flight controller is the indispensable brain of any drone. Without it, the inherently unstable multirotor platform cannot fly for even a fraction of a second. We examined the hardware inside a modern flight controller. STM32 processors from the F4 at 168 MHz to the H7 at 480 MHz, the IMU chip and barometer integrated on board, the communication interfaces, UART for most peripherals, SPI for the high-speed IMU, I2C for secondary devices, the motor output pads connected to ESCs. We explored Pixhawk and the world of open-source autopilots, the platform that emerged from its Zurich research and grew through global community contribution into the backbone of professional autonomous drone operations worldwide. We understood how mission planning, autonomous waypoint flights, and agricultural and survey operations all depend on the autopilot architecture. We distinguished open source from proprietary, understanding the trade-offs, community-driven innovation, and perpetual availability on one side, the convenience and integration of proprietary systems on the other. We went through the firmware layer, what it is, how it differs from hardware and software, how flash memory and bootloaders work, what DFU mode is, and the complete boot sequence from power on to ready to fly. We compared the 4 major firmware ecosystems: Betaflight for FPV racing and freestyle, low latency, manual flight optimized, RDU Pilot for professional autonomous platforms, comprehensive, complex, powerful, PX4 for research and development platforms, clean architecture, robotics-friendly, INAV for long-range navigation drones, the middle ground between Betaflight and Pilot. We broke down the control loop, sense, input, error, PID, mix, output, running 8,000 times per second, every 125 microseconds, faster than any human reflex. We spent substantial time on PID, proportional, integral, derivative, the algorithm of present error, past error accumulation, and future prediction that make stable flight possible. We understood the symptoms of each PID parameter being too high or too low, and why the default values in modern firmware are good starting points for most builds. We traced the evolution of radio protocols from PPM through SBUS and CRSF to Express LRS, and understood why ELRS is the current state-of-the-art, open source, to 24 milliseconds latency, 30 plus kilometers range at minimal cost. We covered ESP now, the ESP32 based direct communication protocol that powers many educational and low-cost drone systems with its advantages of simplicity and accessibility balanced against limited range. We explained binding, the exclusive pairing between transmitter and receiver, and the elegance of the ELRS bind phrase as a password-based approach. We went through all 4 critical calibrations: accelerometer for level reference, gyroscope for zero-rate reference, magnetometer for compass accuracy, escape for throttle response matching, and the specific failure symptoms that each miscalibration produces. We covered fail-safes, the systems that protect your drone when things go wrong, radio loss, low battery, GPS failure, and why configuring and testing them is mandatory. We surveyed the Indian regulatory framework, MoCA at the top, DGCA as the executing authority, Digital Sky as the operational platform, AAI managing airport proximity zones, MHA managing security zones. We went through the Drone Rules 2021 provisions, UIN, RPC, 120 meters AGL, VLOS, daytime only, NPNT, insurance. We walked through the 3 airspace zone colors, green, yellow, red, and understood the real-world consequences of violating each. We reviewed real legal cases, the Red Fort prosecution, airport disruptions, privacy violations, to understand that drone regulations are enforced and the consequences are serious. And we finished with the 10 golden pre-flight rules, your checklist, your discipline, your protection against the gap between intention and reality. Now, what comes next? In Chapter 4, we are going to go deep into drone communication systems. We will explore the full ecosystem of transmitters and receivers, not just the protocols we mentioned today, but the hardware architectures behind them. We will study the radio chips that power everything from a simple ESP32 based beginner kit to a military-grade encrypted frequency hopping link. We will explore long-range communication technologies, understand how telemetry systems work and what data they carry, and look at how commercial drones manage their communication in congested spectrum environments. If today was the brain of the drone, Chapter 4 is the nervous system, the communication infrastructure that allows the brain to receive the pilot's commands and relay the drone's status back. It is a fascinating topic and one that directly affects how you configure and fly every drone you will ever build. Before you close this video, your homework for today. First, open your phone's browser, navigate to digitalski.dgca.gov.in, find the airspace map, and check what zone your home, your school, and your nearest open field are in. Write it down. This is information you need to have before you ever take a drone to those locations. Second, print the 10 golden pre-flight rules card. If your printer is not available, photograph the card from this lesson and save it to your phone. The next time you fly, even in a practice session, run through all 10 rules before you arm. Third, in the comments below, tell me which of the 4 firmware ecosystems you would choose for your first build and why. One sentence is enough. This forces you to actually think through the decision rather than just passively absorbing the information. I will see you in Chapter 4. Keep building, keep learning, keep flying safely.